everybody. We're getting ready to do chapter 12, Transformations and Symmetry of SAT Math Level 2 preparation. And section 12, your notebook will have 14 points in your notebook. And you will have 18 points. So go onto your classwork sheet, have those out. Part 1 of Transformation and Symmetry, Translations, Dilations, and Reflections. Name, date, period, students on your classwork sheet. Due date here for onliners, homeschoolers. And let's go right into page 1 of section 12 in your notebook. The three types of transformations in the coordinate plane are translations, stretches, shrinks, and reflections. Translation preserves the shape of a graph, only moving it around the coordinate plane. Translation is accomplished by addition. Changing the scale, meaning stretching and shrinkage, can change the shape of a graph. This is accomplished by multiplication. And then finally, reflection preserves the shape and size of a graph but changes its orientation. Reflection is accomplished by negation. Suppose y equals f of x defines any function. Y equals f of x plus k translates y equals f of x k units vertically. Up if k is greater than 0, down if k is less than 0. Then y equals f of x minus h translates y equals f of x h units horizontally, right if h is greater than 0, and left if h is less than 0. So let's get into an example here of this. So suppose y equals f of x equals e of x. Describe the graph of y equals e to the x plus 3. So for that one, in this example, k equals 3, so e to the x plus 3 equals f of x plus 3 here, as shown in the figures below. So here's y equals e to the x. And then here is y equals e to the x plus 3. So here's e to the x, here's e to the x plus 3. We go up 3 units on that graph. So the graph of y equals e to the x plus 3 is 3 units above the corresponding graph. Here it's about here, so it goes up 3 on the graph of y equals e to the x. Suppose, for b here, suppose y equals x squared. Describe the graph of y equals x plus 2 quantity squared. So in this example, h equals negative 2 up here. Here's our h. And so x plus 2 quantity squared equals f of x plus 2, as shown in the figures below. So here's y equals x squared. And then here is y equals x plus 2 quantity squared. So we move to the left 2 units like that. So the graph of y equals quantity x plus 2 squared is 2 units to the left of the corresponding point on the graph of y equals x. So again, y equals a f of x stretches, shrinks f of x vertically by a factor of absolute value of a if absolute value of a is less than 1 times absolute value of a is less than 1. So it's greater than, if a is greater than 1, then this would be how the expression will look here. Absolute value of a is less than 1. And then y equals f of ax shrinks, stretches f of x horizontally by a factor of 1 over a if absolute value of a is greater than 1 and the absolute value of a is less than 1. So what does that mean? We'll find out. We'll have an example of that And also y equals the negative of f of x reflects y equals f of x about the x-axis. The reflection is vertical when we have this situation here. A negation of this will be a vertical reflection. And then y equals f of negative x reflects y equals f of x about the y-axis. This would be the reflection would be horizontal in this situation here. And we'll have examples of that as well. Translation, stretching, shrinking, and reflections can be combined to produce functions. Vertical transformations occur when adding, multiplying, or negating takes place after the function is applied, that is, to y. The order in which multiple vertical transformations are executed does not matter. So let's get into one of these examples here. Suppose y equals x minus 1. Describe a graph of y equals 3 times x minus 1. So in this example here, absolute value a equals 3. So 3 times x plus 1, 3 times x plus 1 equals 3 times f of x. So this is x minus 1 here. This is x minus 1 up here. As shown in the graphs below, for x equals 1.5, the y-coordinate of each point on the graph of y equals 3 times x minus 1 is 3 times the y-coordinate of the corresponding point on the graph of y equals x minus 1. So what we do here is we're increasing the slope, and we're also increasing the number here of the for the y-intercept, which is -3. So this would be this graph here changes from this to this. So we've multiplied 3 times this function here. We multiplied it by 3, and this is what happens to it. So suppose y equals x cubed. Describe the graph of y equals quantity 1/2 x cubed. So in that situation, here is y equals x cubed here, and here is a point here, x equals 0.9 right there. Y would equal 0.729 at that point. So in this example, absolute value a equals 1/2. As shown in the graphs below, for y equals 0.729, the x-coordinate of each point on the graph of y equals quantity 1/2 x cubed is 2 times the x-coordinate of the corresponding point on the graph of y equals x cubed. So here is 1/2 x quantity cubed. So what it does, it flattens this out here. On the origin, it flattens the graph out there. X equals 1.8, which is here, then 0.729. So what happens here, this doubles here, and it goes from 0.9 here to 1.8. So this doubles the amount of direction that goes to the right at the same point here on the y-axis, 0.729 when x equals 1.8. So it flattens the curve out, is what it does. When you go from here to here, you flatten your curve out. So E here, suppose y equals natural log x. Describe the graphs of y equals negative natural log x and y equals the natural log of negative x. So, as shown in the graphs below, graph of y equals negative natural log x. Here is natural log x here. And then the negative of natural log x is a reflection here in the x-axis. So as shown in the graphs below, the graph of y equals negative natural log x is a reflection of the graph of y equals natural log x. about the x-axis, and the graph of y equals natural log of negative x. Now this kind of goes in a completely different direction here. Is a reflection about the y-axis. So we start from here and then we go back this way here. So this is a reflection in the y-axis here. And then this is a reflection in the x-axis. Horizontal transformations occur when adding, multiplying, or negating takes place before the function is applied, that is to 2x. Unless an order of doing transformations is specified, these transformations must be taken in the following order: reflect, change the scale, then translate. Moreover, the scale factor, absolute value a, must be factored out of a translation. So let's try one of those. Suppose y equals f of x. Use words to describe the transformation y equals f of quantity negative ax plus b. Observe that all these transformations are horizontal. First, we have to write negative ax plus b as negative a times quantity x minus b over a. The x-coordinate of a point xy on the graph of y equals f of x goes through the following sequence of transformations reflected about the y-axis: horizontally shrunk by a factor of a, or stretched by a factor of 1 over a, and translated b over a to the right. So these are kinds of the machinations that we can stretch and translate and reflect. And I have packets. Students, if you feel like you need review in this, then I can provide you packets for that as well. Suppose y equals sine x. Describe the sequence of transformations to get the graph of y equals sine multiplied by quantity negative 2x plus 1. So observe that all transformations are horizontal. Up here, this is a horizontal transformation. Write the function as y equals the sine of negative 2 times x minus 1 over 2. Consider the point 4 and negative 0.7568 on the graph of y equals sine x. First, reflect this point about the y-axis. So we have negative 4 and then negative 0.7568. Then shrink by a factor of 2, and when you do that, you end up with negative 2 and then negative 0.7568. Then translate 1/2 units to the right. So when we translate 1/2 units to the right, this becomes negative 1.5, and then again we still keep the same y coordinate here, negative 0.7568, and then y1 in this case will equal sine x, and y2 equals sine multiplied by the quantity negative 2x plus 1. So this will be your plot. This will be on your y equals screen and your graphing calculator. Put that in and then hit graph, and you should see that transformation. And the table, so here again showing the points of 4, negative 7.568 for y1, and then negative 1.5 and negative 7.568 for y2. So that would be your transform. That would be your table shot there of what that would look like. Reflections about the x and y axes represent two types of symmetry in a graph. Symmetry through the origin is a third type of graphical symmetry. A graph defined by an equation in x and y is symmetrical with respect to the x-axis of replacing x by negative x preserves the equation, and the y-axis of replacing y by negative y preserves the equation, and origin of replacing x and y by negative x and negative y respectively preserves the equation. So these symmetries are defined for functions as follows. Symmetry about the y-axis, here's an example of that. F of x equals the f of negative x for all x. Symmetry about the x-axis will be f of x equals the negative f of x for all x. And then symmetry about the origin be the f of x equals the negative of f of negative x for all x. As defined previously, functions that are symmetric about the y-axis are even functions, and those that are symmetric about the origin are odd functions. Let's get an example here. H, discuss the symmetry of f of x equals cosine x. Since cosine x equals cosine of negative x, cosine is symmetric about the y-axis, making it an even function. However, since cosine x does not equal negative cosine x, and cosine of negative x does not equal negative cosine x, the cosine function is not symmetric with respect to the x-axis or the origin. I, discuss the symmetry of x squared plus xy plus y squared equals 0. If you substitute negative x for x or negative y for y, but not both, the equation becomes x squared minus xy plus y squared equals 0, which does not preserve the equation. You have a big change here because of this sign. Therefore, the graph is not symmetrical with respect to the axes. However, if you substitute both negative x for x and negative y for y, the equation is preserved, so the equation is symmetric about the origin. So that would be a quick answer to that. And again, I have packets that I can provide for review on this subject matter of translations and odd and even functions, etc. Contact me for that. And that is lesson 12, SAT Math Level 2 Prep, animated PowerPoint math video at AOL.com for questions or course materials. Thank you very much.